Alright, so welcome back. So now we're going to be looking at, in polar coordinates, the problem of area, finding area in polar coordinates. How do we compute area if we're in polar coordinates? Well, we're not going to go back to parametric form because we didn't even talk about area in parametric form. Rather, we recall some facts from trigonometry, and that is if you have a circle, radius r, and you have a sector or slice, if you will, of the circle that we're looking at, a sector of it, and we want to compute that area, we can use a result known as the sector area formula for a circle. And what that says is that if you have a central angle theta in radians, then the area is just 1/2 times theta times the radius squared, of which of course you're familiar, pi r squared area formula is just one special case. So for a sector of a circle, we can compute the area by taking 1/2 the angle in radians times the radius squared. Okay. So how does that help us out? Well, if we have some curve in polar coordinates, say we were looking just in the first and second quadrants, looking in the first quadrant, we had some curve in polar coordinates that, there it is, r is some function of theta. It can be simple or complicated. And we wanted to compute that area. And the knowledge we have is r as a function of theta. Okay. How would we compute that area? Well, what we can do is subdivide. That's what we've always done. Subdivide our interval up, except now we're subdividing around the variable theta. So we're subdividing the angles. So we'd have an angle here like theta 1, another angle here, theta 2, and so on throughout the whole thing. Right? We would just keep going. And every one of those, we would approximate it with a circular sector. Right? We would approximate the area with a circular sector. Okay? And so we would have, different little angles there. And so then we would focus on just approximating the area just for one little sector. Right? We focus on doing it for one little sector because that's what we did. We subdivide it. We focus on just one sector that we want to approximate. Okay. We would then add them all up, take the limit, which would turn it into an integral. Okay. Subdivide, approximate, add, limit, integral. Right? And so that's what we're going to do. So on our one interval, right, let's say that we're here. Again, we don't know exactly what the function is doing. It could be doing something, kind of a little complicated, a little ugly there, but we're only worried about what's going on with our approximation. And our approximation would have some radius r sub I. Right? I guess actually technically if it's r sub I, it should be over here. On the left, this would be ri minus 1, the other radius, which would be slightly different. And then we'd look at the size of the interval. That would just be the change in our theta variable. That would just be how much theta changed across from the last interval. So that our approximation would be that a sub I, the area for the ith sector, is just 1/2 the radius r sub I squared times delta theta I. Okay, we then add all those up, which would turn it into a sum. We take the limit as the size of the largest subinterval goes to 0, which would transform this into an integral. So we would have this result here. is that if r was equal to f of theta, then the area would be the integral from the first angle spot in radians to the second angle spot in radians of this stuff, 1/2 f of theta squared d theta. Okay, and so this would be our integral formula for finding the area in radians. Now, it's very important that when you're doing these, that you're measuring from the center out, and the radial function is whatever that distance is from the center out. Okay, this is important, measuring from the center out. This is important if we're looking at areas involving more than one radial function. Some area between two regions or something like that, which we'll get to a little bit later. But we're measuring the area, the length from the center, the origin, out to that place. We're measuring that radial length as a function of theta. Okay, so there is our area formula, and we're going to look at using this in some upcoming examples.